Welcome to Learn with us. This is the 14th lecture of Basic Electronics.
First, we will have a quick review of our previous lecture. In your last lecture, you studied how diode acts as a clipper, and you also understood different types of clipper circuits with the help of examples. What are the learning objectives of this lecture? In this lecture, you will solve some examples of shunt or parallel clipper circuits. In this lecture, you will also understand breakdown region of diodes, and here you will study about Zener diodes. From our previous lecture, we know that this is the configuration of parallel or shunt clipper circuit, where this is RL and here we have V0, here we have Vi, and this is R1. Okay. In my previous lecture, I have mentioned that when this diode is off, then we will use VDR for finding output voltage, and its formula is RL divided by R1 plus RL, and this term is multiplied by input voltage. Okay. Now, if this R1 is very small as compared to RL, then in that case this output voltage will be equal to input voltage. Okay, so we will use this assumption for solving our upcoming examples. Okay, now look at this example. If you have a circuit like this, where now this diode is connected with a DC battery, and here we have load resistor RL, and the voltage drop across this resistor is V0. This is R1, this is plus minus V, and for suppose here this is of 5 volts and this is Vi. So if your input signal is something like this, where this is positive Vi, and for suppose in this case it is 10 volts, and this is negative Vi, which is minus 10 volts. So how you are going to start your analysis? Again, you will look at the direction of diode, and we know that when diode is connected in this direction, then it will be on during negative half cycle of the input signal. But again, here this additional DC battery is also connected. It means this circuit is biased, and this battery will also affect this diode. So here first we will find transition voltage, and we know that in case of ideal diodes, the condition of this transition voltage is Vd is equal to 0 and Id is equal to 0. So if we apply this condition to this circuit, our circuit will look like this, and we know that here we have V0 plus minus, this is plus, this is minus, this is Vi, and this is R1, this is Vd, and this is plus minus 5 volts. Okay, now look at this loop. If we apply KVL here, then our KVL equation will be minus VI. This terminal is positive, this is negative, and this is positive, plus VR1, because here the voltage drop across this R1 is VR1, and minus VD plus V is equal to 0. We know that in this direction current is flowing, which is ID, and if we look at this condition here, VD is 0, and from Ohm's law V is equal to IR, so here this VR1 is equal to IDR1, and we know that this ID is 0, it means this whole term is also 0. So now this equation will become minus Vi plus V is equal to 0, or Vi is equal to V is equal to 5 volts. So this is your transition voltage. Okay. Now if you look at this circuit, we know that this diode will conduct during negative half cycle of the input signal, but since this anode is connected to this positive terminal of the battery, it means now this battery will make this diode forward biased. Okay, so this diode will be off only when the input voltage is greater than this transition voltage, and if this input voltage is less than this transition voltage, then this diode will be on, because this DC supply will be pressurizing this diode to stay in the short circuit state. Okay, so the input voltage must be greater than this transition voltage, which is 5 volts, for the diode to be in the off state, and any input voltage which is less than this transition voltage, it will result in a short circuited diode. Okay, so this is the transition voltage in this case. We know that this is our circuit here, and here we have V naught plus minus, this is Vi, and this is DC battery V. Now what would happen during positive half cycle of input signal? Now as you can see, this diode is connected in this direction. It means this diode will be off or reverse biased by this input supply voltage Vi, but this diode will be on or forward biased by this DC battery. Okay, so as like I have discussed in my previous slide, that when this V in is greater than V, then this diode will be off, and when this V in is less than V, then diode will be on. Okay, so now when this diode is off, then the circuit will look like this. Okay, It means now this current is flowing directly towards this output voltage. Okay, so if we apply assumption here that this R1 is very much less than this RL, then we know that in this case output voltage is equal to input voltage. Okay, so this is our output voltage in case of positive half cycle. Now what would happen during negative half cycle of input signal? Now in this case we know that this terminal will be negative and this terminal will be positive. So in this case this diode will be on or forward biased by input supply voltage, and again it is on or forward biased by this battery. Okay, it means now in this case it will be forward biased by both input supply voltage and the DC battery voltage. Okay, so in this case your circuit will look like this. Okay, plus minus, minus plus VD 5 volts V naught. Now in order to find V naught we will apply KVL in this loop. So our KVL equation will be minus 5 plus VD plus V naught is equal to 0. It means here V naught is equal to 5 volts. Okay. So what would be your output waveform in this case? We know that our input signal was like this, and if this is our transition voltage which is 5 volts, we know that when V in is less than V, that is 5 volts, diode will be on. Okay, it means from this point to this point diode will be on, and when this diode is on, V naught is 5 volts. It means this would be our output here, and again from this point to this point V in is less than V, so again up to this region this diode will be on, that is 5 volts. Now if diode is off, it means when this V in is greater than V, then our output voltage is same as input voltage. It means here we have this sort of waveform. This is the output voltage during positive half cycle. Now during negative half cycle we know that this output voltage is 5 volts. So the signal is drawn like this. Okay. Now if I draw this output waveform separately, it is like this, where this is 5 volts and this is 10 volts. Okay. Now we know that this circuit is clipping negative half cycle of the input signal. This circuit is biased and configuration is parallel. So this circuit is an example of shunt negative clipper with positive bias voltage. Why positive? Because this positive terminal of this DC battery is connected with this positive terminal of the diode. Okay. Now look at this example. If you have a circuit like this, where we know that this is RL, and here we have V0, this is Vi, this is R1, and this is DC battery. And again we assume that it is of 5 volts. So if your input signal is like this, where this is plus Vi and it is 10 volts, and this is minus Vi, which is minus 10 volts. Okay, so how you are going to start your analysis? We know that this diode is connected in this direction. It means it will conduct during positive half cycle of the input signal, but again here this DC battery is also connected, which will also affect this diode. So first we will find transition voltage in this case, and we assume that in case of ideal diodes, our condition is Vd is equal to 0 and Id is equal to 0. So this circuit will now look like this. And now this is plus minus Vd, this is plus minus R1, this is the direction of current, this is plus minus 5 volts, and here we have load resistor, and voltage drop across this load resistor is V0. Okay, now in this case our KVL equation will be, this is VF minus VI plus VR1 plus VD is plus 5 volts is equal to 0. Okay, we know that here this Vd is 0 and this VR1 is also 0 because it is equal to ID R1, and here ID is 0. So now we have Vi is equal to 5 volts. Okay, so this is our transition voltage. Okay, now if you look at this circuit, here when this input voltage is less than this transition voltage, then diode will be off, and when this input voltage is greater than this transition voltage, then diode will be on. Why? Because here now this positive terminal of the DC battery is connected with the negative terminal of this diode, and this positive terminal of diode is connected with the input supply voltage. Okay, so if this input supply voltage is less than this V, then this diode will be off because it will now affect this diode more, and when this input supply voltage is greater than this V, then this diode will be on. Okay, so this is your transition voltage in this case. We know that here our circuit looks like this. Okay, and here we have load resistor, there we have V0 plus minus, this is Vi, R1, RL, and this is plus minus 5 volts. Okay, now what would happen during positive half cycle of input? Means if this terminal is positive and this is negative, then this diode will be on or forward biased by this input supply voltage, and if you look at this side, then this diode will be off or reverse biased by this DC battery, okay, that is 5 volts. And we know that when V in is less than V, this diode is off, and when this V in is greater than this V, then this diode will be on. Okay, so now when this diode is on, then this circuit will look like this. This is positive, this is negative, and we have V naught here. This is plus, this is minus. Here we have VD, this is plus, this is minus, plus, minus 5 volts, plus, minus. Okay. Now if we apply KVL here in this loop, then our equation will be minus 5 volts minus VD plus V naught is equal to 0, and in case of ideal diode this VD is 0. It means here V naught is equal to 5 volts when during positive half cycle of input signal, when this V in is greater than V. Okay. Now what would happen during negative half cycle of input? It means when this terminal is negative and this is positive, then this diode is off or reverse biased by this input supply voltage, and again it is off or reverse biased by this DC battery. It means now here this diode will be reverse biased by both of these voltages. So in this case, this circuit will be like this. Okay, here we have V naught, R1, RL, and here again we assume that this R1 is very less as compared to this RL. So in this case, our output voltage is equal to input voltage. Okay, when during negative half cycle of the input, when this diode is off. Okay, so what would be your output waveform here? We know that our input signal was like this, and our transition voltage was 5 volts. Okay, so when this input voltage was, when it was less than 5 volts, then we know that this diode is off, and when this diode is off, output voltage is equal to input voltage. It means from this region to this region, this would be our output voltage. Okay, it means here V naught is equal to VR. Now after this point, when this V in is greater than V, that is 5 volts, then this diode is on, and when this diode is on, output voltage is 5 volts. It means this is drawn like this. Okay, so this is our output voltage during positive half cycle of the input. Now what would happen during negative half cycle? During negative half cycle, V naught is equal to Vi. It means during negative half cycle, this would be your output waveform. This is minus 10 volts, this is 5 volts. Okay? And if we draw this output waveform separately, it looks like this. Okay, this is 5 volts and this is minus 10 volts. Okay, now as we can see, this circuit is clipping positive half cycle of the input signal. So it means it is an example of shunt positive clipper with positive bias voltage, because here this positive terminal of this battery is connected with this diode and this configuration is parallel. Okay, now here is your class task. If you have one circuit like this, where this is load resistor RL and here we have output voltage V0 and this is R1, this is Vi, this is minus plus V, that is DC battery. This is your first circuit and then you have another circuit which is like this, and here we have load resistor RL and here we have V0 plus minus, this is DC battery, this is R1 and this is Vi. Now this circuit is an example of shunt negative clipper with negative bias voltage, and this is an example of shunt positive clipper with negative bias voltage. And here V in both of these circuits is 4 volts, and if this is your input signal where this is plus Vi and it is 16 volts and this is minus Vi which is minus 16 volts, then what would be your output waveform in both of these circuits? Okay, this is your class task. Now if you remember current voltage characteristic curve of real diodes, it was like this, where this x-axis was voltage and this y-axis was current, and here we had this curve in forward biased region, and here we had a curve like this, and this region is reverse biased region, and this is breakdown region. Okay, this axis is negative V and this is negative I. Okay, now we will talk about breakdown region of diodes. We know that this is current voltage characteristic curve of diodes, where this is forward bias region, this is reverse bias region, and this is breakdown region. As you can see, diodes in breakdown region follow two mechanisms. One is Zener effect and other is avalanche effect. In general, diode junction breakdowns occurring at -5 volts are caused by the Zener effect. It means here this Zener breakdown is occurring at -5 volts, whereas breakdowns occurring at voltages more negative than -5 volts are caused by the avalanche effect. In general, this avalanche breakdown usually occurs at -7 volts. This Zener effect is also known as field ionization, and this avalanche effect is also known as impact ionization. Now, what are Zener diodes? Zener diodes are also called breakdown diodes. They are silicon semiconductor devices that are designed for operation in the reverse breakdown region. The breakdown voltage of a Zener diode is set by carefully controlling the doping level during manufacture. Now, what is the symbol of this Zener diode? This is the symbol of this Zener diode. As you can see, instead of a straight line representing the cathode, the Zener diode has a bent line that reminds you of the letter Z. Now, here this anode is the positive terminal and this cathode is the negative terminal of this Zener diode. What is the difference between Zener and normal diodes? In normal diodes, the breakdown voltage is very high. These normal diodes get damaged totally if a voltage above the breakdown level is applied. But in case of Zener diodes, the breakdown voltage is not as high as normal diodes, and these Zener diodes are not permanently damaged if a voltage above the breakdown level is applied. Now look at this. We know that this is the symbol of a normal diode and this is the symbol of Zener diode. It shows that the symbols of Zener and normal diodes are also different. Now we will understand the circuit diagram of Zener diodes. This is the circuit diagram of Zener diodes. As I have mentioned in my previous slide that the Zener diode is employed in reverse biasing, and we know that in reverse biasing the n-type material of the diode is connected to the positive terminal of the battery and the p-type material of the diode is connected to the negative terminal of the battery. We know that in n-type material, electrons are the majority charge carriers and in p-type material, holes are the majority charge carriers. We also know that opposite charges attract each other. It means electrons from this region are attracted towards this positive terminal of the battery and holes from this region are attracted towards the negative terminal of the battery. And due to this attraction, this depletion region will become thick and in this region more positive ions will be created, whereas in this region more negative ions will be created, and we know that due to these ions in this depletion region electric field is generated, and under the influence of this electric field there will be flow of minority charge carriers. We know that in p region electrons are the minority charge carriers and in n region holes are the minority charge carriers. So under the influence of this electric field electrons from this p region will move towards n region. Okay, so what would be the direction of current here? This would be in the direction of current, and here the current is saturation current or drift current, which is due to minority charge carriers. And in this case, we know that due to this thick depletion region, there will be no flow of majority charge carriers, and we know that due to the movement of these majority charge carriers, diffusion current is generated. So it means in case of reverse biasing, saturation current is greater than diffusion current. Okay, so this is the working of Zener diodes. Why these Zener diodes are useful? These Zener diodes can conduct in both directions. It means this Zener diode permits current to flow in either a forward or reverse direction, which is very useful for creating voltage references, shunt voltage regulators, and overvoltage protection circuits. The ability to keep the reverse voltage across its terminals essentially constant is the key feature of these Zener diodes. A Zener diode operating in the breakdown region acts as a voltage regulator because it maintains a nearly constant voltage across its terminals over a specified range of reverse current values. These Zener diodes provide a constant output voltage to a load connected in parallel to it, irrespective of variations in the energy drawn by the load or variations and instability in the supply voltage. So that's all for today. Now, what are the key takeaways of this lecture? In this lecture, you solved some examples of shunt or parallel clipper circuits. In this lecture, you also studied about Zener diodes. You understood their circuit diagram. You studied the difference between normal diodes and Zener diodes. And you also understood why these Zener diodes are useful.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.